Hello, everyone. My name is Nathan Peck. I'm a developer advocate for Amazon Web Services in the Container Services division. And today I'm going to present on architectures and strategies for building modern applications on AWS. So let's start with some level setting. What is a modern application? So let's consider some characteristics of a modern application. The first is that it's container-based. And the reason why this is important is, we'll discuss this in more detail, but containers offer you a way to have reproducibility, transparency, and resource isolation in your architecture. And we'll go into how to actually deploy this in a modern application stack. Second key primitive of a modern application is that it's dynamically managed. So in the old days, a lot of times when you ran an application, you would put it on a box that was in a server room somewhere or in a closet somewhere, and it would sit there 24/7 for maybe even years. The new modern application stack, though, is much more dynamic. We actually have applications that scale up and down. They run for a few hours and they shut down, and something else runs on the server stack that used to be running that application. And then the third primitive of a modern application is this microservice oriented. And we'll talk about some of the benefits of microservices and the reason why this is a core aspect of building a modern application. But just to summarize, microservices, they give you the ability to limit the blast radius of any bugs. They allow your organization to develop code faster and more reliably and get features out the door more quickly than if you were not using microservices. So summarizing these three different characteristics of the modern application, I want to actually change that term modern to cloud native. Many of you are probably familiar with the Cloud Native Computing Foundation. These three primitives are actually core primitives of the Cloud Native Computing Foundation's description of a modern application stack as well. And so a modern application is primarily first a cloud native application. Building cloud native has a lot of very significant benefits for your application. I want to go over three in particular, though. The first is speed. So when I'm developing a new application stack or a new feature, what is the time to value? The time from here's my idea to here's my idea actually running and giving value to me and to my customers and the people who are keeping my business supported. Additionally, how fast can the team innovate when circumstances change? So let's say your organization needs to pivot, or customers are asking for a new feature to be added to the application. How fast can you actually answer those demands of the market when you need to? And a cloud-native application should have the ability to scale. So once again, this is a request from the market, a demand from the market, that the application that started out maybe just running on a few servers, maybe now it has tens of thousands of users that are using it constantly and concurrently, and we need to be able to scale to handle any load at any time. And then third, the cloud-native application is resilient. So it's capable of responding to all sorts of different disaster scenarios that may pop up, all sorts of cases where maybe someone's trying to attack the application with a denial of service attack, or someone pushed a bad code to the application, and the part of the application stack is at risk of crashing, maybe as a memory leak. A cloud-native application is capable of being resilient even under these less than positive circumstances. So let's look at the building blocks that bring about that speed, that scale, and that resiliency. Key building blocks for success in the cloud-native environment all starts with containers and functions. So the old sort of model of thinking about an application was thinking about the application as code. But in the modern stack, we recognize that an application may start with code, but it's not composed solely of code. For example, let's say you're running a Python application. You're going to need to have your Python interpreter, a Node.js application, the same thing. Many modern applications have a full stack that has dependencies, a runtime engine in addition to the code. And all of these components fit together, and they need to be the right versions. They need to interact with each other correctly. And so when it comes to building this application, you can't just stop at the code. You have to consider not only the code, but the environment that's necessary for that code to run. And you need a way to package that code up in a way that will produce consistent results when you go to execute it. And so this is what a container and a function, serverless function, for example, in Lambda offers. And so we're going to go into how containers and functions can benefit your organization and different tools for running them on AWS. The second key building block for a cloud-native modern application is the cloud itself. So we're going to talk about some of the benefits of the cloud relative to traditional data center deployments. And we're going to talk about how it's important to actually use the cloud to its fullest capability. You can't just lift and shift and then not actually take advantage of the capabilities of the cloud if you want to have that successful modern application stack. And then third is there's the actual people aspect. So it's one thing to have the containers and functions running in the cloud, but you have to have the people who are capable of running these containers and functions, making sure that they are high quality and really feeling a sense of responsibility for the entire stack. So we're going to go into each of these three areas. But first, let's start with those containers and functions. So a lot of you have probably heard of the 10 times developer, the 10xer, if you will. And this is kind of the legend, perhaps. Maybe it's based partly on fact, maybe it's just an exaggeration, but the idea that there can be an engineer who is so much more effective than his or her peers that they can produce as much value as 10 of their peers. But what if I told you that there was a 440xer? So in a recent Puppet State of the DevOps report, they found that fast companies are 440 times faster than the slowest companies. And this massive gap in capability and speed goes across a number of different stats. So in terms of code deployments, we see fast companies have 46 times more frequent code deployments. That 440 times number, it comes from the lead time from commit to deploy. So a programmer writes code and commits it into the code base. The fast companies get that code out to customers 440 times faster than the slowest companies. Fast companies, when they have downtime, when something has gone wrong with their system, they're 96 times faster to bring that system back up and back online for their customers. And then this is also a very important rate. They have a 5 times lower change failure rate. So whenever they make a change to the system to add a new feature, to add, revise a feature, update something, their changes are 1/5 as likely to fail and bring things down for their customers. So when you see these stats, you can see that there's this wide range of capabilities, and that's because there's such a wide range of different technology in use and different tools for deploying that technology and building those technology stacks. And this really puts things in perspective, especially in the Silicon Valley area. It helps you understand how, in some cases, these small startups that are using a stack that allows them to be 440 times faster are able to compete against large established companies that maybe don't have the same efficient modern application architecture. The core to success at being that 440 times faster company is that of shipping features and not just code. And there's a lot of different ways that this applies to how you go about the development cycle. But we highlighted how containers and Lambda functions are a key portion of that very beginning of the modern application architecture stack because it's more than just the code. It is the entire application stack as a component that you can deploy. And because the container contains more than just the code, it has everything that you need for a particular feature. And what we find with organizations that deploy containers and Lambdas is that they have this ability to have a reproducible stack, they have the ability to roll back, and they have the ability to know that the code that works locally on their local machine is going to work in the staging environment, it's going to work on the production environment, and the feature actually makes it through the pipeline, not just a specific code commit. The feature encompasses the entire stack, including the runtime and the dependencies. So let's look at a graph about how containers enable fast deployments. You'll see this graph is very interesting. From 2014, 2015, then through 2016 and 17, you see a tremendous gap develops between the high performers and how many deployments that they do per year, and the low performers and how many deployments they do per year. So back in 2015, high performers only really had about 4 times as many deployments per year as the high performers only had about 4 times as many as the low performers. Then you see in 2016, that gap widened significantly. And so why that happened? Well, we started to see in 2016, 2017, wide adoption of containers across many different organizations. And so containers enable fast deployments because it gives you this reliability, this ability to know that I've built my container and I'm able to push it out across all these different environments very quickly and very reliably. That also goes to how changes can be immutable and rolled back. So for example, look at this graph on the left. That's the mean time to recover if you were to push some code in a container to your environment, and that code was buggy and was causing crashes. How fast can you recover from a failure? And you'll see that this massive gap developed in 2017 between high performers and low performers. Now, does this mean that engineers somehow got worse in 2017 at the low-performing companies? It actually means that more and more companies began adopting these modern practices that allow them to become high performers. And so now that gap has widened, and the long tail of extremely low performers has become even more evident in 2017 than it was in 2016. Companies are migrating to containers in order to get that mean time to recover down, and in order to benefit from the advantages of that modern stack. Once again, you see the same thing with change failure rate. The companies that are high performers have much lower failure when they do an update to their system. So this leads into the cloud native principle number one, which is that a cloud native application enables a high functioning organization to build and ship features faster. And the reason why they're able to build and ship features faster is because they're using modern tools such as containers and lambdas that give them reliability, that give them the confidence that they need to actually build things and get them deployed to their production environment without worrying about it breaking everything. So now moving on to the second key building block for success in a modern application stack, that is the cloud. And when the cloud and cloud adoption was first beginning, a lot of companies felt that they could just take whatever they were running in their local data center and just move it directly into the Amazon cloud, into VMs, and just do a one-for-one copy of how their architecture worked in their local data center. But they quickly found that they didn't have all the same benefits that they expected compared to organizations that built from the ground up in order to take advantage of the features of the cloud. And there's a number of those features that I want to highlight. The first is pay-as-you-go. The cloud allows you to only pay for the resources that you use. The second is self-service. The cloud allows you to spin things up without needing to be responsible for waiting on someone else. You don't have to wait on someone else to answer your requests. You talk to an API and you get what you need. And then it's elastic. You can use what you need, and then you can shut down what you don't need. So let's look at the story going back to kind of the dark ages of the data center native architecture. It used to require that you would have a facility, either you build it or you rent it, and you would have to purchase these servers and actually move them into the data center. And once they were in there, you would need to maintain them. They would need power and cooling and cleaning even. You don't want those cobwebs on your servers. And they lived for years. It was very hard to innovate when you were tied to an expensive server that you purchased and that you now need to use for the next 3 years. And so this led to the cloud migration, where people began moving their things out of the data center into the cloud. And one of the core reasons why they did that was because the old data centers, you had to pay up front, and you would depreciate that value over the next 3 years. In the cloud, you pay a month later for the number of seconds that you actually used in that last month. And so what this allows you to do leads into the cloud native principle number 2, which is this modern application stack. If it's a modern application, you only pay for what you used last month, not what you guess that you're going to need in the next year. What this allows you to do is allows you to make decisions faster. You don't have to sit down and plan out where you think the business will be in the next year. You can rather plan out where you want the business to be in the next week, and you can provision the resources that you need for that week, and you can shut them down when you don't need to, and you don't have to worry about, well, we bought a lot of expensive servers and then it turned out we didn't need them. All of this allows your teams to experiment and fail fast without significant investment. You don't have any sunk cost. You don't have any regrets if you run a new stack for a month as a test and it doesn't work out. You just move back to the old stack again, or you try something else, and you only pay for what you used in that 1 month. Now, another aspect of the old system before the cloud was when you wanted architecture, or you wanted services, you wanted machines to use for building your application, you had to file tickets and wait for every step. After all, if you're going to actually order a physical hardware server, you're going to have to order it. It's going to take time to ship. It's going to take time to install. It's going to take time to make sure that it's actually working and getting cooled properly, getting enough electricity and network. In many cases, this would take days or even weeks. In the cloud native architecture, everything is self-service and on-demand. People can interact with an API and get what they need when they need it within minutes. So the reason why this is important is not just because it's more convenient to be able to get things fast, but it's important to make sure that your organization is actually taking advantage of this to its fullest. Some organizations, they're too used to this kind of slow process of dealing with filing tickets, and so they end up adopting that same type of mentality when it comes to the cloud, and setting up, for example, someone who's operations, who's in charge of setting up the architecture, and you need to file a ticket with them in order to set up something on your AWS account. And they end up introducing this negative aspect of the old on-premise architecture into the cloud and actually holding the developers back. So cloud native principle number 3 is that a modern application architecture that's cloud native is going to enable all their developers to do things via APIs and automation. You shouldn't have request tickets in order to get something accomplished. You should have everything you need at your fingertips and the permissions you need to create what you need, and the tools empower your teams to work without being blocked. Another major characteristic of a modern application is its use of elasticity in the cloud. So old school data centers, it was hard to get over 10% utilization on those data centers because occasionally there would be a huge peak. And when that happened, you needed to have lots of spare capacity to absorb it, but the rest of the time you didn't need that capacity. And so you ended up running at maybe 10% utilization. Now compare that with the cloud, where most organizations are able to get up to 40% utilization. In some cases, I've talked to customers that say they get 80% utilization on their instances. The reason why they're able to do this is because they're confident that whenever they need another instance to run their application on, they can just add it to the pool of available resources, and when they don't need it, they can remove it, and they can play much closer to that margin when they want to. And this has some significant benefits. It's the reason why it's cloud native principle number 4. A modern application is able to turn off when it's idle. It's able to scale to workloads of any size. You're able to get much higher utilization out of the resources that you do provision for that application. And all of this adds up to be huge cost savings. You don't spend nearly as much money when you have fewer resources and higher utilized resources. A cloud-native application should also be resilient. And there's a few aspects to a resilient application. One of them is the blast radius. When something bad does happen, how do I stop it from cascading and taking other things down? Well, the answer to that is loose coupling and geographic distribution. So we'll talk about what these aspects mean in the cloud-native architecture. So blast radius is something that is really enabled by microservices. With a microservice, you're able to take one of your business components, one of your business features, and it becomes its own specific service, which is independent of other services. And when it does need to communicate with other services, it does so through loose coupling. Rather than having a hard dependency, it should be capable of disconnecting from the other services when needed and continue to operate to the best of its ability, even when conditions are not ideal. Now, what this allows you to do is it allows your teams to move quickly and independently when they're deploying code. So ideally, in a loosely coupled microservice environment, a service team that is responsible for delivering a feature could actually deliver that microservice prior to its other dependencies coming online because of loose coupling. So perhaps the service comes online and only one or two of its dependencies are available. It will continue to talk to those two dependencies and gracefully fail out things that is not yet available. And so this ends up with a very interesting architecture where a team is able to deploy as soon as their piece is ready, and then as the other pieces come online, the connections between them are established, and the feature is actually able to reach its full maturity once all dependencies are available. Additionally, this microservice architecture ties into blast radius, because if a bad code commit is pushed to one of those services and it does start to fail, it goes down. The other services continue to work because they're isolated and because they have that loose coupling. And microservices tie in very nicely with geographic distribution. So AWS currently has 18 regions, 53 availability zones. There's this capability to deploy microservices in different places where they're as close as possible to the end user. And one of the interesting patterns that we're seeing is some things are very hard to geographically distribute, other things aren't. But microservices allow you to distribute the things that are easy to distribute to the different regions, and then keep the things that are hard to geographically distribute, perhaps in a central region, which is the brains of the entire worldwide operation. But because you're using microservices, you don't have to worry about distributing everything to every region, but you can distribute maybe something that's client-facing, like maybe there's a lightweight messaging system that's responsible for having a WebSocket connection to get RPC messages from a client to another client quickly. That part could be distributed worldwide while your core API, which maybe handles user accounts, is in one region. Microservices allow you to take full advantage of these regions rather than worrying about every single piece being geographically distributed. You can distribute the things that you do want to distribute when you want to distribute them. So cloud native principle number 5, use microservices, basically. They reduce the blast radius. They improve your mean time to recovery when there is an issue. And they help you to establish a globally distributed deployment model by making it easier to distribute only one piece of your application when you need to. Moving on to the third key building block for success in a modern application architecture, that's the people. It's the culture of the organization. The containers and functions, the cloud, they're all great, but you need great people who will actually be able to make use of these things to their fullest. And I want to present a few different ideas about how this can work. The first comes from Adrian Cockcroft. He's currently working as the VP of Cloud Architecture Strategy at AWS. And he said, you don't add innovation to a culture, you get out of its way. And so the idea behind this is that you can't force a culture, you can't force an organization to be innovative, but you can look for what is stopping innovation, what's holding people back from innovating, because at the core, most organizations do want to innovate, they do want to update and use new things, but something is holding them back. Let's look at a couple more ideas. This is one thing that may be holding people back. It's the idea of Conway's Law, that a team will build software that matches their organizational structure. So if your organization is very top-down, it's very tiered, there's a lot of layers of business communication that go into any decision, it's likely that what ends up being built is a very heavily tiered application that has a lot of layers, has a lot of communication back up and down those layers. On the flip side, if your business organization is composed of small, agile teams that are able to build independently, you're going to end up with a team that is very successful at building microservices. So what Conway's Law means is that when you go to look at how you want to build your architecture, you have to also consider how the team structure works and make sure that those two match each other. Because the large monolithic organizational strategy will have a hard time building microservices, and conversely, small agile teams will have a hard time building a successful monolith. You need to make sure that the organizational pattern matches the software pattern that you're trying to develop. The next idea for culture comes from Werner Vogels, who you probably saw at the keynote this morning. You build it, you run it. So this came about early on in Amazon and Amazon Web Services with the idea that any team that is building something should also be responsible for the operational details of how that thing gets run. And the reason for that is that engineers like to produce good code, but sometimes if they're not in charge of operations as well, they won't have visibility into what's really going on with their application. You end up with a disconnect. If you have engineers who are working on software and then you have an operations team that's responsible for deploying it and managing it in production, then the operations team could be seeing significant performance issues and crashes and issues that are stopping that application from being successful to customers, but the engineering team isn't necessarily in the loop about that. Or if they are, there's a delay. It could take days before the engineering team is able to fix an issue. With the you build it, you run it style of software organizational strategy, the engineers are actually put on the pager. They're actually on rotation whenever something goes wrong with this software component. They're notified right away. So this is something we developed and we use extensively at Amazon. Even managers are on the pager, and they get paged whenever there's an issue with availability or crashes with a service at Amazon Web Services. Works very fantastically to make sure that engineers will deliver high-quality code and make sure that they are able to fix issues as quickly as possible. The next idea I want to present comes from Nora Jones. If you've never had the pleasure of hearing her speak about chaos engineering, I highly recommend it. She speaks quite often at different events. But she's the senior chaos engineer at Netflix. And she talks about a method of thinking about software where you don't plan for if something is going to happen, you plan for when it happens. And basically the idea is don't necessarily count on prevention from stopping an application from crashing. Plan for that application component to crash and actually force it to crash to see what happens. And so this style of thinking about application availability led to Chaos Monkey, which is a Netflix framework for actually deliberately crashing and shutting things down on your Amazon account to see if your architecture is resilient. Can it restore itself when it breaks? Will customers see an impact if this one random machine gets terminated? Ideally, the answer is no. They should not. And so this book also is very fantastic about chaos engineering. It talks about how to really develop that mindset and how to engineer things for chaos to happen so that it can restore itself very quickly. So reviewing these principles of the modern cloud-native application, it starts with containers and functions. This is an ideal modern architecture pattern for packaging your application up and running it. It continues to the cloud. The cloud provides the place in order to run all these containers and functions. And then equally important is the culture, the people who will actually be operating those containers and functions in the cloud. So the modern application architecture includes how you run and interact with it, how it integrates with other services, and how you monitor it. The how you run and interact with it, that kind of covers the code, the containers and the functions, the code, where the code is actually running. How it integrates covers the cloud, because the cloud provides the integrations to your containers and to your Lambdas so that they can connect to other cloud services and other components that are running in your cloud. And then how you monitor it is how you provide your people with a culture of observability into what's going on in the organization and in the software that's running in their cloud. So starting from the left-hand side from that run and interact, let's talk about the first way that you can run and interact something in your AWS cloud. That's AWS Lambda. So AWS Lambda provides an event-driven serverless system for running a function. And it could be Node.js, Java, Python, C#, or Go. And you can even bring your own libraries, including native ones. A lot of people don't actually realize that you can take a binary, an arbitrary binary, and put it into your Lambda function and execute it. There's a lot of power there. You could literally run anything that you want to run inside of that Lambda. And Lambda is extremely flexible. It's designed for both synchronous and asynchronous use, and it integrates with other AWS services, including API Gateway, which provides essentially an HTTP interface that will forward any web requests that hit it to one of the Lambdas that's hooked up to a route on that API Gateway. In terms of the cost and resource that we talked about earlier as being a fundamental part of cloud-native architecture, Lambda has an extremely simple resource model. So you select a power rating. It's based on the number of megabytes of memory that are available, from 128 megabytes up to 3 gigabytes. And based on how much memory you select for that function, you're going to get an amount of CPU and network capacity. Additionally, we provide flexible authorization, so easy ways to give that Lambda and the code running in it permission to talk to other resources on your account, such as DynamoDB table, Aurora, or similar. Lambda is designed for people to be able to use it easily. We offer a number of different ways to edit the code, including Cloud9, which is the WYSIWYG editor. Or you can use your own custom tool, and you can upload a zip package to Lambda. And we provide plugins for Eclipse and Visual Studio to also do this automatically. The programming model is very similar to what you're used to using on a regular computer. You have processes available. Like I mentioned, you could put an arbitrary binary into that Lambda and execute it. You can use threads. You can use /temp. You can use WebSockets when you need them. And you can use the same AWS SDK that works on your local development machine or on VMs or containers. Lambda also provides a lot of visibility into monitoring and logging. Not only metrics for the requests, but metrics for failures. And all the logs, everything that happens inside that Lambda that you log will go into CloudWatch logs. It's also really designed for a stateless architecture. So this is another aspect of the modern application architecture is the idea of statelessness. Rather than counting on something being written to disk and then reading it back from disk, you persist it into an external storage engine that's designed for persistence. And with the stateless architecture, you actually have no access to the underlying infrastructure as a feature. You can't SSH into any local box and modify things because there are no boxes, essentially. You just have running code. So let's look at one of the customers that's been successful using AWS Lambda, which is FINRA. They're the Financial Industry Regulatory Authority. And they process a daily influx of 37 billion records having to do with financial trades. And they check for things that don't follow the established regulations for the financial industry. The quote here is pretty amazing. They said, using AWS Lambda, we've increased cost efficiency by a factor of 2. And just to give you an idea about how much that means, FINRA performs 500 billion validations a day using AWS Lambda. So obviously, if they're increasing cost efficiency by a factor of 2, there's a lot of savings to be had there. So here's the architecture that they chose to deploy. They have incoming files to be audited. They upload those files to an Amazon S3 bucket. And then the Amazon S3 bucket triggers an event which causes Lambdas to be executed to pull those files out, process the trades and financial transactions that are described in those files, and then write the results back via an SQS queue that's being listened to by an EC2 instance. The EC2 writes summary information to an RDS deployment, and then consumers are able to interact with the controller and pull that data out when they need it. So this system, as I mentioned, is highly scalable, handling 500 billion validations a day, and they're very happy with the cost as well. Let's look at another tool that we provide, Amazon Elastic Container Service. So this is designed to make it easy for you to run a container on the AWS cloud. It offers features such as container-level networking. We have service discovery now as well that allows each of your container tasks to have its own IP address and to be registered in a service discovery mechanism where containers can talk to each other using host names. ECS offers deep integration with the rest of the AWS platform. So it makes it easy to give different containers that are running on the same EC2 host access to different resources. This is huge for security because it allows you to have one service that maybe is communicating with an S3 bucket to store user-uploaded images, and another service is communicating with a sensitive database that has credit card information. And they may be running on the same machine, but they have access to different resources. You don't have to grant global access to everything running on that machine. Additionally, ECS allows you to deploy things globally. We have global footprint in many regions around the world. Auto-scaling, CloudWatch metrics, and integration with different load balancers. One successful ECS customer is McDonald's. And I probably don't need to introduce what McDonald's is, but let me share some stats. They have 37,000 restaurants, 1.9 million employees in 120 countries, and they serve 64 million customers a day. So they decided that they wanted to build a global platform to connect customers and delivery services with their restaurants. And they wanted this to be deeply integrated worldwide with whatever the best food delivery partner was in that particular area. So if you ever use Uber Eats to order McDonald's, you've used this system. In building this, they had a few critical business requirements. The first was speed to market. They wanted to be able to build this system quickly. The second was scalability and reliability. McDonald's serves a lot of customers, and they wanted to be able to handle up to 500,000 orders an hour with this system. They wanted multi-country support, so they wanted this to be able to be deployed worldwide, and they wanted to easily be able to integrate it with different food delivery partners around the world. And then the last was cost sensitivity. Obviously, one of the nice things about McDonald's is it's very affordable, but that means that any system that McDonald's uses needs to be very cost effective because the margins are low. So in tackling these challenges, they chose a few key architectural principles. The first was they were going to use microservices. This would allow them to build many different integrations with different partners. It would allow them to easily distribute those integrations worldwide to different regions, where perhaps in the United States, the integration talks to Uber Eats, maybe in another country, it uses a different food delivery service. They would use containers and orchestration with ECS to actually run these different microservices worldwide in different regions. They wanted to use platform as a service offerings whenever possible. What this meant was they wanted to use key AWS platform components like ECS, SQS, RDS, and Elasticache rather than trying to run their own services, because this would allow them to build quickly and efficiently. And they wanted to build both synchronous and event-based models to push orders as well as provide APIs that provide synchronous responses. So here's what they ended up building. Once again, you can see Amazon ECS is there at the heart of the system, powering each of the microservices. And you can see how they've tied in different AWS services into the heart of their system to connect to the menu and restaurant systems, to connect to the third-party delivery platforms, and to connect to their McDonald API middleware. So the results of this architecture was they were able to build the entire system in months. Once again, we're looking at an organization that has a 440 times speed efficiency here. They were able to build this worldwide system in months. The reason why is because ECS offered a simplified DevOps platform that took them from nothing to successful ability to deploy a container quickly. And they're able to now integrate with all these restaurants and global delivery partners, handling 20,000 transactions per second with sub 100 millisecond latency. And most importantly, it's also very cost effective, so they can run this system and offer delivery to people without worrying about it costing a lot of money. Now, in working with customers like McDonald's who want to deploy on ECS, we've realized that a lot of customers were more focused on running the application than the platform. After all, the platform may be interesting at first just to learn about how to deploy containers, but fundamentally the most important thing, especially if you're trying to be one of those 440 times faster organizations, is that application that you're delivering to your customers. And so we want to enable a closer focus on the application and less of a focus on the messy details of how the platform actually gets deployed across the cloud. So that's why we introduced AWS Fargate. So Fargate offers the ability to run an application in a container by specifying how much CPU and memory you want available to that container, and then you just forget about it. You don't have to provision an EC2 instance. You don't have to worry about what EC2 instance the container got placed on. You don't have to worry about if it crashes or if an EC2 instance gets taken out of service, because that container is always running, and if it stops or crashes, it will come back up again automatically. So you can scale from just one running container to thousands of containers without provisioning a single EC2 instance on your account. So the core goal here was to provide this easy-to-use, powerful consumption model to offer resources for containers without any instances to manage, with a container-native API that was really designed from the ground up for containers to be able to connect to the other AWS resources without any changes to your Docker container. And finally, for the pricing to be resource-based rather than based on EC2 instances. Approaching the problem, obviously, running a container locally is easy. You can just spin it up with the Docker run command. You can stop it with the Docker stop command. When you go to run containers across EC2 instances, though, you start to get a little more of a challenge. You have to actually communicate with these EC2 instances to run these tasks. And so in the old model, it looks similar to this. With ECS, you would run an EC2 instance, and there were a number of things on that EC2 instance that you were responsible for managing, such as the Amazon machine image version for the EC2 instance, because that contained the Docker engine, and that contained the ECS agent that communicated with ECS. And while this is certainly simpler than manually logging into a box and spinning up or down Docker images manually on that instance, there was still a lot of things that need to be maintained and upgraded. Let's say the new version of Docker came out that had a security fix. You would need to patch that instance across your cluster. So the ECS system, offering these different availability zones and offering the scheduling and orchestration across them, was our starting point. We took those instances and we decided to actually replace them with Fargate. And so with this operational model, we were able to talk to the ECS scheduling API and just ask ECS to run a container, and ECS will run the container in Fargate without needing to add an EC2 instance to your account. It's very easy to get started. You can actually use the launch wizard, first launch wizard, to launch an Nginx box or launch an example PHP application and see it working, and use that as a starting point for your application. So I encourage you, if you haven't tried this out, to just log into the console and try launching a Fargate container. Once again, as we talked about granular pricing, you're able to shut this container down at any time when you're done with it. So you don't have to worry about it costing a lot of money. You can play around with this new service and just test and see how it works. So I want to share one customer who's been very successful at using AWS Fargate, and that's Product Hunt. Once again, a lot of you are probably familiar with Product Hunt, but they are one of the premier websites for curating different products and startups that launch. They provide a way for the community to vote on different products and vote them up to the top and provide feedback and really discover interesting new products that have launched. So Product Hunt, their entire website runs as microservices. They use Ruby on Rails and GraphQL behind a Node.js front end. And they wanted to take these microservices and migrate them into AWS Fargate. Because they wanted to be able to scale quickly without worrying about EC2s, they want to be able to schedule multi-container workloads where different containers communicate with each other. And they wanted to have robust controls between which containers can talk to other containers. So they decided to go all in on AWS and AWS Fargate in January 2018. And they were able to move this application stack over very quickly because AWS Fargate offers this simplified resource model that doesn't require a lot of learning. And Fargate, for them, has helped them deal with traffic spikes. They started out running a baseline of 25 tasks, but as traffic blows up, let's say one of the products becomes very popular, they're able to scale it up very quickly. Here's what their application architecture stack looks like. We have the end consumer who's communicating with a CDN, and that CDN is hooked up to an externally facing ALB, application load balancer, which forwards the incoming traffic to one of various different microservices that are responsible for generating web pages and serving different tasks that are part of the website. You can see that each of these different services, such as the back-end web external or the front-end web external, is a polyglot application. So for example, one of them could be running Ruby on Rails. One of them right there you can see is running Node.js. And you can also see that it's a multi-tier application. So these different Fargate containers that are running different application stacks, they communicate across two tiers. There's the externally facing ALB that handles external facing website. And then there's an internal ALB with a background task that's internal and handles internal API things. You can also see that there is, interestingly, a job queue. So some of the tasks that they have are, for example, scraping websites or generating cards for website. They want to do that asynchronously behind the scenes. And so they use Ruby on Rails Sidekick queue, and they use background workers that also run as AWS Fargate tasks. And they can scale each of these different things independently. So if they have a large queue of background websites to scrape, they can fire up as many background workers as they need in Fargate. And if they have a large influx of consumer traffic, they can scale up one of these front-end facing Fargate tasks. And once again, all backed by Redis and PostgreSQL. So the quote from Fargate, the quote from Product Hunt, we moved to Fargate because we need the ability to scale quickly up from baseline, run multi-container workloads, and get fine-grained network control without having to manage our own infrastructure. So this is what AWS Fargate has delivered to them, the ability to use all these things like AWS security groups and application load balancers and VPCs alongside their containers. Now, the next tool I want to talk about in terms of deploying your code in a modern application stack is Elastic Container Service for Kubernetes, EKS. So we announced this at reInvent as a managed Kubernetes control plane. Basically, a lot of our customers were running Kubernetes, running into challenges with scaling Kubernetes, running into challenges with, for example, managing the etcd data store behind Kubernetes. And they asked us to start running that Kubernetes control plane for them. So we've developed EKS as a way to provide this premier experience for Kubernetes on AWS with native AWS integrations to all the AWS services that you're familiar with. We're doing this all open to the community. So everything that we will build for Kubernetes, you'll see open source. We joined the CNCF as a way to join the Kubernetes project and make sure that we're not just forking Kubernetes, we're actually writing code that can be contributed back to anybody who wants to run Kubernetes, whether it's in AWS or in an on-premise data center or in a different cloud entirely. We're offering on-demand upgrades for your Kubernetes clusters. So this used to be a challenging problem. How do I upgrade my Kubernetes cluster? Well, now EKS will do that and handle it for you automatically. And one of the most important things is it's highly available by default. So running a highly availability Kubernetes across different availability zones used to be a bit of a challenge, especially when it came to etcd. EKS basically handles that. And so just an idea of how EKS works, you provision a cluster using the console, and it gives you back a cluster endpoint. And that cluster endpoint can be associated with your kube control, so that way you can communicate with the cluster masters to request that tasks be launched or shut down or upgraded. And then you can also spawn any number of worker nodes that register themselves in those masters as a pool of resources to be available to run your containers across. So by communicating to that kube control to the cluster master will then tell one of your EKS worker nodes to run the task. And you can continue to run more of them. One of the important things about this is that we're also announcing the ability to launch tasks using Kubernetes onto Fargate. So this is something we've announced for 2018, but the ability to actually use kube control to talk to your Kubernetes master, and your Kubernetes master will actually have the ability to ask Fargate to run the container instead of needing to talk to a worker node that you manage as well. So once again, recapping the features of this EKS platform, we're offering everything that's needed to have conformance as well. This is another important one. Many of our customers need PCI or HIPAA compliance, and EKS comes with that. Application orchestration can be a challenge sometimes. We announced AWS step functions as a way to help a modern application stack become automated and really able to react to changing situations. A lot of times when there is an availability scenario or something that has changed about your application architecture, it may require the intervention of a human to make a decision. But whenever that's the case, you could also consider, is it possible for me to build automation that could make the decision about what to do here? And so we have AWS step functions as a way to help you with these workflows where you have a challenging situation, such as running out of capacity in, let's say, your EKS cluster, or perhaps your ECS on EC2 cluster runs out of capacity. You need to be able to scale that up. Step functions provides a tool for building out these workflows for resolving these scenarios automatically. And in terms of giving your engineers visibility into what's going on, we also provide Amazon CloudWatch, the ability to capture metrics on all of your different resources, act on those metrics. If the metrics go over a certain threshold, maybe trigger an SMS or a PagerDuty alert. Analyze them by looking at dashboards or summaries of the stats over a certain time period. And another thing that we announced that we're very proud of is AWS X-Ray. So this tool provides the ability to analyze and debug your performance by visualizing all of your interconnected pieces of your application and seeing how the network communication flows between them and what type of latency or error conditions there are. So this is very powerful when you combine it with, for example, Lambda functions and containers in a hybrid architecture. Because you're able to see those network connections. You can see this Lambda talk to this container, and the container maybe kicked off another Lambda invoke. And here's my latency between each of these different components. And the long tail of perhaps you see that 50% of the requests are fast, but then another 50% are extremely slow. And you're able to see that and diagnose it. So after reviewing all these different components, I just want to review one more time the key building blocks for success in a modern cloud-native application. It starts with the containers and functions, because these are the tools that you use to package that code up and make sure that it's going to run effectively in the cloud. It continues with how you utilize the features of the cloud to provide auto-scaling, to provide integrations with other services, and capture metrics, for example. And it also includes the culture. It includes how you have the people who are maintaining that code and the tools and processes that you make available to them. The goal of all this is to provide you with the ability to build whatever you want and to build it fast. So thank you very much for your attention. And if you get a chance, please complete the session survey in the Summit mobile app. I'll leave the instructions up here for how to actually provide feedback on the session. Thanks a lot.